quiet. No speak. You be quiet. No speak. You be quiet.
Hey guys, if you are watching, we are getting ready for ChaserCon 2020. It is coming up here momentarily. And we're going to leave you guys with a slideshow of very quickly a couple images from some of the storms in Virginia and some of the storms that have been chased over the past couple years. And we've got our special guest today, Dr. Jeff Halverson, who is coming up in just a few minutes. Again, you are getting ready to watch a virtual version of ChaserCon 2020. And you'll learn more about derechos today, which is a topic on a lot of folks' mind. We've had a lot of famous ones in years past, and we'll talk more about that coming up in just a little bit with our special guest. We'll let folks join in. We'll let everybody join in and we will get started here momentarily. We got our panel of folks on getting ready to hear more about derechos. Of course, remember the one we had back in 2012 here in the Mid-Atlantic, which was a popular one, of course. There's been many since then that may be less memorable for us here in Southwest Virginia, but we've got a broad audience watching today. So we'll be learning more about those, many others, and also why they form too, which is going to be an interesting conversation. So thank you guys for tuning in. We'll let everybody join in here and we will start this in just a second. Here's some kids there in the background. All right, Chris, would you like to introduce our special guest today? It looks like we've got some folks on and we will get this started.
Yes, well, thank you, Brent. Well, welcome everybody to the 2020 version of Mid-Atlantic Chasercon. Obviously, we're meeting virtually this year for reasons that we can't control, but so we're going to miss rubbing elbows with everybody, but this does give us an opportunity to reach out to a broader audience. As a matter of fact, I have it on good authority that we may be even having some folks joining us from the UK, from across the pond. So that's kind of fun. The other thing that it gives us the opportunity to do is to have television stations here in Virginia help us co-host. And of course, you've already heard Brent Watts, who's the chief meteorologist from WDBJ7 in Roanoke, Virginia. And the next several weeks, the next several sessions, we'll have 1 hour sessions each week, starting today for the next 3 weeks following, will be hosted by different television stations. So that's kind of cool to give us that chance. But today we want to introduce Dr. Jeff Halverson, who's a professor at the University of Maryland, Baltimore campus. And he is a severe weather expert. For those of you that follow the Capital Weather Gang, a very popular weather account, he is their severe weather expert. He's written dozens of papers, written and co-authored dozens of papers on severe weather. And he currently follows a lot of the severe events here in the Mid-Atlantic and does some analysis. Today, he's going to talk to us specifically about derechos. He'll be talking about how they form, but the specific event he'll be speaking of happened in June of this year, 2020, in Pennsylvania and New Jersey. So, Jeff, welcome to the program.
Well, thank you very much, and good morning to our audience. We certainly appreciate you coming in, taking interest in severe weather awareness research. and what a spectrum of things we experience in the Mid-Atlantic through the course of the year. I can't think of a more weather diverse region in the United States than what we have to put up with in the Mid-Atlantic. But one of these fearsome kind of storms is a summertime storm for us, mainly Dayrachos. And I'm going to go ahead and share my screen here. And I hope everyone can see my very first slide, which is the title slide, Mid-Atlantic Dayrachos. And in particular, after a brief introduction of Dayrachos in the Mid-Atlantic in general, we're going to focus in on a very interesting case from a few months ago, back in early summer, up in pretty much the whole state of Pennsylvania and much of New Jersey and out into the Atlantic. So this is a very, very fascinating storm that did a lot of damage. It killed people, and it was one of the more memorable ones of the past couple of decades. And so my talk outline, we'll start everyone off, make sure we're on the same page, understanding what exactly do we mean by Dayrachos. And we'll give you a little bit of a historical perspective of these storms in the Mid-Atlantic region. Then we'll dive right into this case study. We'll start by looking at an overview of the system from radar and in terms of the wind damage that it generated. And then, of course, we always want to look at how are these events being forecast and warned. And historically, these could be a bit tricky to identify their initiation and how long they're going to last. And one of the big concerns in the Mid-Atlantic is, particularly if you're east of the mountains, are these things going to survive crossing the Appalachians? And some do and some don't. And we want to understand what are some of the key discriminators for that. Then we'll look at I got some nice loops here to share with you, some lots of satellite imagery, lightning, radar. And then I want to go into what I call multi-scale analysis, which kind of starting off with the synoptic scale. What was it that triggered this system? This is actually a very, very early morning system, which makes it very interesting. And then what we call the mesoscale, which is kind of the middle scale of space and time. Some of the things that I believe may have contributed to the ferocity of this event. And then finally drill down a bit into some of the fine scale radar structure, a few interesting facets of that. And then we'll conclude with the lessons learned. And I believe we'll have time at the end for some Q&A on this. So I'm just going to proceed through the talk. If you have questions, just kindly hold them for the end. So I want to start off by saying that this year so far has been a very big year for Dayrachos in the United States. And this is a listing of 9 of these Dayrachos. Now, it's not so uncommon to get as many as 9 or 10 of these across the United States in a given year. But what I think makes this year very memorable is the geographic spread of these events. If you look at some of these, and you see the Pennsylvania, New Jersey there on June 3rd, we had one cross the Great Lakes on June 10th. We had, now this June 6th, that was very interesting. This thing came across the Rockies and had over 1,000-mile trajectory right across some extremely mountainous, semi-arid terrain of the Western US, and then cut into the Northern Plains and places like Utah and Colorado. And the thinking is this may have been what we call a low dew point derecho, which means that the dry air can actually promote the evaporative cooling and accelerate the outflows of the storms and produce quite a windstorm as a result. But then we have kind of, classic Great Plains derechos in June and July, in the Dakotas, Minnesota, et cetera. And here's this oddball one, October 7th, up in New England, which has been proclaimed a derecho by the National Weather Service up there. This was a system that originated in upstate New York, in central New York, and it cut across and really hit central eastern New York very, very hard, and then into New England with a lot of those wind gusts above 70 and causing quite a bit of damage to trees up there because trees were still in foliage up there. So altogether, it's been a very, very active and dynamic derecho year. So let's define this creature. And this is a term that was introduced back in the late 1900s by a meteorologist, I think also chemist as well, by the last name of Heinrichs. And he coined the term to mean straight ahead. I believe this is a Spanish derivative word that means straight ahead. And to distinguish this from the rotary storms known as tornadoes. Of course, we didn't know much about what the heck was causing either of these back in the late 1800s, but at least people could make a distinction between a small scale wind that was rotating and a straight line wind, and both of which could cause extreme amounts of damage. But the problem is with derechos, various kind of official definitions exist here. You've got definitions of these in the AMS glossary, and you have a lot of different definitions in the research literature. And some may say, well, it was it or was it not a derecho, and that's always a tricky thing. And it's hard to ascertain whether you're dealing with an actual derecho in real time as this thing's unfolding, because one of the main criteria is a length criteria. A swath of 400 miles, right, is what people typically look for. And when this thing's in progress, it's hard to make that determination if it's going to indeed be a 400-mile long continuous swath of wind damage. But the mechanism is we are looking for straight line winds and the combination of really intense gust front and downbursts, and lots of downbursts, and clusters and families of downbursts that keep erupting from the convection as it travels along. Derechos can occur all throughout the year, and they do. We get cold season derechos, but you typically tend to see those down in the Gulf Coast region, where you've got some instability over the warm water that can feed and sustain these systems during the winter months. But probably the most destructive ones and the most widespread and frequent ones are those of summer. And those are extended. I'll show you a slide across the upper Midwest through the Great Lakes and into portions of the Mid-Atlantic New England. There's a corridor there that's been very well defined and shown in the climatology. And these are perhaps the most violent derechos. I do want to mention a very, very violent derecho in the Midwest. I should have mentioned this in the previous slide. Matter of fact, let me go back to that. This is, let's see here. This was the Northern Plains derecho. No, the Midwest derecho, August 10th. This is the one you may have heard about that cut across Iowa and did, now the estimate is this come in close to $6 billion worth of damage, which makes it the costliest single thunderstorm event, convective event ever in U.S. history. This thing did a number to the central portion of that state, and a lot of that damage, folks, was agricultural. And we're talking corn. This is a corn belt of the country, a lot of soy out there as well. But the devastation was near total, even to structures, well-built structures, frame structures, and of course the number of trees. There were fatalities, and they are still very much recovering from that event. It really set back the economy of the state. And of course, all this occurring in the midst of COVID. How do you handle, a response and sheltering as a result of something like that? But this event's going to be talked about for a long time. The wind gusts generated, there were several observed gusts in excess of 110 miles an hour with this, and estimated gusts up as high as 140. And one thing people remarked about this derecho is that the high winds came up and they didn't stop for an hour. So imagine being subject to, extreme wind gusts. It's as if basically a hurricane eye wall came through. And that's the kind of the level of damage that was experienced out there. So we'll go back here to the definition. So widespread, long-lived, convective windstorm, straight line winds, swath of 400 miles, widespread severe wind gusts, 58 plus. That's how we define a severe wind gust. Okay, we like to see these being measured. Okay, and you want to see these widespread along that swath. And this is where the definitions vary a bit. Some of the definitions require at least two or more widely separated, what we call significant gusts, which are 75 plus mile per hour gusts. Other definitions don't adopt this, okay? And the mechanism here, bow echo, one or more bow echoes, and I'll show you what those are in a coming up graphic here, but this is an arc-shaped, rapidly moving line of deep convective cells that's very long-lived. The thing regenerates, and the thing typically propagates along 50, 60, 70 miles an hour. I think the one out in the Rockies this past year was clocked at 100 miles an hour for some of the lifetime. So this is a nice graphic I put together that shows the initiation, the growth, and the maturity of a derecho producing system over many hours. And you know, you have to have a trigger for these things, and it's usually a very, very super intense line or cluster of thunderstorms that starts going severe very, very early. And then it starts putting down a significant cold pool or cold downdraft. And that develops a small area of high pressure at the ground. We call that a meso-high. And as the system begins propagating, typically to the east or the southeast, the bow echo, the convective line or arc, enlarges, it expands, and it's continuously being regenerated by uplift of warm, unstable air along that gust front. And the downdrafts merge together. You're starting to get downbursts being generated now. And that cold pool is starting to really expand and have some teeth in it. And the meso-high is getting stronger and stronger. So as this thing moves along and propagates, and now you see hours later, the cold pool has become very extensive. Here you can see individual downbursts are firing off within the convective elements. This is a storm complex, unlike a supercell. A supercell is a rotating thunderstorm that is dominated by the rotating or the helical updraft. It's organized around that rotating updraft. A derecho, that bow echo, is being organized and driven around a very, very strong downdraft. So it's a very, very different type of system. It's the downdraft here that is central to the intensity of the system, the regeneration of the system, the propagation of the system, etc. These things can go 900,000 or more miles, which means, you know, it's a 18-hour plus affair, and these things will cut across many, many states. And I guess the one good thing about the forecasting, once this initiates and holds together, a lot of times the high-res models will start picking up on these and start doing a decent job. And you often will have a few hours to warn. I remember the 2012 derecho, the infamous one here on June 29th. We had several hours advance warning that the thing was going to become a problem for us east of the mountains during the late evening hours. And I think we did a pretty good job getting the warnings disseminated for that one. Okay, so that's a bit of the physics of the storm. Now what you see here is a climatology of summertime derechos. And this is just to put the Mid-Atlantic in some context here. This comes from Guastani and Bozart. Is a very recent paper, and Monthly Weather Review is a very outstanding review paper of derecho climatology. And this is this belt or this arc of high derecho frequency in the summer months. You see that originates in the upper Midwest. There's Iowa, okay? Right across Chicago is the maximum across the southern lakes into the Ohio Valley, okay? And now what you see is well, hang on here. The interesting thing you'll see is abrupt drop-off in the frequency of these events right where the Appalachians are. And that's really no surprise, because the Appalachians often along the ridgeline, you have an air mass that may not be as unstable because of altitude effects, but also it could be that the high terrain is disruptive to the outflow and can disrupt the balance of dynamics in these systems. Also, as if the systems are crossing in the evening, in the overnight hours, once the systems get east of the mountains, we think they'll collapse and die because you're just in the diurnal minimum of unstable air. You know, the air mass tends to be stable at night by the time these things arrive. So whether or not these things survive the crossing of the Appalachians, a lot depends on their timing, we're finding. And that's tied to the diurnal cycle of heating and cooling. But there may be some other influences, including the effect of the orography that could be disrupting things. So there's a lot of unanswered questions there. Now, here's a little bit of a history of some of the more outstanding cases since about 1980. This case of July 4th, 1980, you can see it initiated in Iowa. And this is the very, very long swath here of damaging wind, and all the way to the Chesapeake Bay. So from the interior of the United States over, probably nearly 1,000 miles here, right out to the Atlantic Ocean. And the red numbers are showing the peak gusts. And all along the trajectory that you're seeing, you know, exceptional gusts. You've got an 81 in Ohio, you've got an 81 here in Virginia, and this is just one long continuous damage swath. Here's one from 2003, August 26. I'm not showing the damage swath here, but at least I can show you a radar snapshot. This one came basically from the northwest across Pennsylvania down across Mason-Dixon, and did a lot of tree damage here in the DC Baltimore area, knocked out power for a lot of people for 3 to 5 days. And of course, this is just a few weeks before Isabel hit, right? So that was a really, really rough late summer, early fall for us. Now this other one here to the right, this is a much more detailed radar snapshot of one on June 4th, 2008 that came in from the west. You can see the very characteristic arc of the bow echo, and there's embedded kind of mini bows within the larger bow. You just get the sense that this thing is being pushed out by a very, very strong cold pool and a meso high, and that really are the key dynamics that are propagating this and creating the significant wind damage. Now, of course, everyone's favorite down here on the bottom center, the infamous June 2012, that's called the Ohio Valley Mid-Atlantic Dayrachos. That's its official name. Got to start. Look at that. Good old Iowa. Okay. And this thing really, really started to expand and elongate when it got into Ohio. And now this is a day when we had one heck of a heat wave in the I-95 corridor. Got to 104 degrees that day in DC. Now, this derecho was a rare one that did survive the Appalachians, and it came late in the evening. It survived, and we think the reason it did that is because there was such an unstable air mass that had been built east of the mountains because of the very high heat and humidity. Those of you who understand what convective available potential energy is, or CAPE, the dullest sounding that evening measured a CAPE of almost 6,000 joules per kilogram east of the mountains. Now that's at 8 in the evening, folks. And we knew that, okay, geez, that is a powder keg of dynamite. And when what was ever left of that derecho hits that, it's going to blow. And sure enough, it had no problem sustaining itself across the Appalachians. And then finally, over here in the lower right is an interesting day in 2013, June 12th, 13th. 2 derechos. Look at this. One coming down out of Iowa once again, cutting across the Mason-Dixon. This one kind of fizzled as it crossed the Appalachians. There was not nearly the amount of CAPE east of the mountains that evening when it came through. But then on its heels, the next day, this very impressive line swept across, largely across Virginia, North Carolina, and actually produced something we call the ICC tornado up here in Maryland. There's this we call intercounty connector. It's a 22-mile long, I think, F1 that was generated in one of the vortices in the bow echo. So that's, you know, we could talk for hours about these various cases. What I really want to do is get the focus here now squarely on June 3rd. And this is a radar montage or composite showing snapshots of the derecho as it cut across Pennsylvania. And look at this early morning initiation, right? And over Lake Erie, get this. This is a lake initiated line of storms, 6, 7 in the morning. But instantly, as it comes off, you start to see very, very tall, intense cells, probably 60 dBz here in upper northwest corner of Pennsylvania. And then just the continued expansion, and ultimately really the most intense phase of the storm, 11 o'clock, noon, 1 p.m. And that, by the way, is a very unconventional time to get hit by a very severe windstorm. And I think that caught a lot of people by surprise, even though this thing was adequately warmed, as you'll see. It's just the timing was a bit strange for folks. But really, the most severe gusts were here over southeast PA, all the way across New Jersey. And it's very interesting to see this thing maintain its form so far offshore over the Atlantic. And really could still identify this thing well into the mid-afternoon, a couple hundred miles out over the ocean. But here we see path length 500 miles, easily meets the criteria for derecho. And now what we'll do is just a bit of a synopsis here. So we're calling this a single bow echo type. We call this a progressive type of derecho, where you have a single intense bow echo, and average forward speed about 70, maximum peak, get this, 83, 93 mile an hour gusts. And we'll show you where those were. Fatalities, 3 in the Philadelphia area, 4 total. 500,000 power outages. Yeah, you certainly expect that with something like this. About 250 official log damage reports at the Storm Prediction Center. And we've already, brought up the fact that this thing crossed the Appalachians, survived, did really well on the east side, and peak intensity came at a very unconventional time. Okay, and we'll get more into that, why that happened. Now, this is a map that shows individual damage, observations, and the colors indicate different wind speeds here, different thresholds. The red boxes are wind gusts that are approaching 90 miles an hour. And you see, really, if you trace back to Erie, hardly anything documented up here in terms of damage. Then a couple of isolated reports around 8 or 8:30 in the morning, and just a few intermittent reports. Now, there could be more reports here than what we're showing, because this is a very rural area. You're up here on the Allegheny Plateau, and not a lot of people live up here. And so if you're not around to hear the tree fall, doesn't make it sound type of thing, right? So it's the same thing. If you're not around to observe a damaging wind gust, did it occur? So we won't ever really know probably what the true extent. There's maybe an undercount here, but what I think is very apparent is when this thing comes off the Allegheny, off the Blue Ridge here, the Blue Mountain along Harrisburg up to the Lehigh Valley, it just goes nuts, and it really starts producing a very high density of damaging wind reports. You don't want that happening in a major city like Philadelphia, but it nailed Philadelphia very strongly. And then right out here, really the strongest gusts were along the Jersey coast. And now let's look at some of those wind gust values, putting some numbers to those colors. So you see back around Philly, several gusts in the 70 mile an hour range. We'll go all the way back to Reading. Look at that, 83. Okay. But now look at the coastline, 70, 89. And there's a couple on here that were over 90 that aren't being shown here for some reason, but very high density in this corridor. Now let's look at the outlook and the warnings. How was this handled by the pros? And this is Storm Prediction Center did a pretty good job, I believe, forecasting the probability of a long-lived windstorm. Excuse me while I blow my nose. I am suffering from ragweed allergies this morning, driving me nuts. This is the convective outlook from SPC, issued 06Z. So this is the wee dark hours of the morning. They put this out, and this is interesting to see an enhanced area. We don't get these too terribly often here in the Mid-Atlantic, but an enhanced is going to be a day where you really have got to look out. And this is the verification. So the blue dots are showing where all the damage was clustered. The black squares are the significant gusts over 75. And this really is to SPC's credit. They kind of nailed this. I mean, this is a very well done convective outlook. Okay. Now, the question here is, could you have justifiably put out, let's say, a moderate risk as opposed to an enhanced? That's a tough call after the fact. I think based on what they knew going into this event, with the parameters that were likely to evolve later that day, maybe their thinking was on the border of enhanced or perhaps moderate. Maybe they said, well, we'll make that judgment later in the day. But I think at least getting an enhanced out there was a very good call on their part. And then the warning was done very well. Now, this is out of the Mount Holly office, which handles very large piece of Pennsylvania, Jersey, Philly, et cetera. And they did a great job getting the warnings out. This is type of products they're putting out on social media that day, showing an actual radar snapshot. Look, here it's coming. There's no mistaking you guys in Southeast PA, New Jersey are going to get whacked by this thing. Take your precautions for this. It's coming, using language like extremely dangerous situation, seek shelter now. they did a good job. And that's the one saving grace about these things. Once they're formed, we can see them coming, we can warn. But whether or not they're going to trigger or initiate, that's the tricky thing. And we would love to give people at least 24 hours notice that we think the next day is going to be a derecho day, which we really don't do very well at that. We can identify that there is a corridor of meteorological conditions, dynamics, thermodynamics that would favor a derecho, but we can't really say a day or two in advance, yeah, one's going to fire, and this is the time, and this is the intensity, and so forth. So there's a lot of work and a lot of research that needs to be done here with regards to the 24 to 48 hour, perhaps 72 hour time frame on these events. Okay, now let's go ahead and look at a radar. Everyone should see this animation here. This is the complete sequence of the storm, and just look at this thing. Really evolves a classic bow structure. We'll replay this a couple of times as it advances across Southeast PA. See, it's very linear as it comes across the Allegheny Plateau, but you can see the outflow really starting to dominate over Southeast PA and literally pushing the front end of that line out ahead of the northern and southern ends, causing that very characteristic bow shape. And that's a very, very strong meso high that's driving that. And the other interesting thing, is it develops kind of an asymmetry here as it comes across New Jersey. And by all appearances, it looks like there's a meso vortex that is formed, a cyclonic vortex that's formed up on the northern head of this thing. And that's very, very common with these bow echoes. In fact, there was probably what we call a set of bookend vortices attached to the northern and southern end of the line. They're just hard to see in the radar, but those things probably existed for a few hours. But typically what happens over time, the Coriolis effect, basically the spin of the Earth begins to influence the northernmost vortex most strongly, because that's the counterclockwise rotating vortex. And so the Coriolis effect will help intensify and enlarge the northern side vortex, and that becomes kind of a dominant feature in these storms. Let's go to this slide here. Now, this is a sequence of different satellite views, and what you're going to first see here is visible satellite. This is rapid scan imagery of this thing marching across, and I'm going to pause it there, okay, and go back and let you look at that again. It all happens very quickly, but look at the initiation over the lake, just towering convective cells. You can see them bubbling up, overshooting tops, very, very massive, very impressive on the visible imagery, and also the very rapid motion of this thing. Now let's continue the animation, because now we're going to go into, this is lightning density from the GOES satellite. And this just shows continuous firing of lightning as a thing. Let me go back. It comes across the state. One of the interesting things that there's early on, there's quite a high density of lightning. See this cell right here? This thing really, really fires off with something very, very deep, very, very tall, and very super intense. And this is 8 a.m, right? So that's one of the very interesting facets about this. One does not expect basically severe thunderstorms to erupt at this time, particularly in close proximity to a cool lake. This is summer, folks, and this lake water is a lot bit cooler than the surrounding land as you start to heat up in the morning. Okay, but the system does maintain itself very nicely, and then you can see the lot of lightning here into the southeast, and here is the infrared, and this is probably the most impressive. Simply look at the mass of cloud being generated by all that convection. That to me is something that's very, very telltale about the updrafts in these storms. For this enormity of a cloud shield to be generated and to spread over such a large area talks about something called mass flux, and what's coming up is spreading out and moving away. When you see this amount of condensed water spreading away so rapidly, those updrafts, those chimneys, those vertical conduits have to be incredibly strong to be putting this much mass into the upper atmosphere and causing an expansion like this. But you know what? The 2012 event a little bit further south looked just like this. As a matter of fact, it was even more massive than this. So you don't get the sense of the bow echo by looking at the satellite. But when you see something really circular like this with extremely cold cloud tops, these are probably minus 75, minus 80 degree turrets in this deep convection, you're dealing with something that truly is exceptional. And here you see the convection much better defined, this little area right here. But this is the area that's feeding this massive cloud shield. Okay, let's move on here to, I like this one. This is a rapid scan, and I'm just focusing on this as a final animation. This shows you now the boiling convection and look at this anvil casting the shadow here. That is one tall complex. Look at the bubbling convection. The little red W's are the wind reports that are being generated as this thing moves through. And you'll just see the wind reports go nuts out here in a couple of seconds. Look at the convection bubbling up. What an astounding, and you see gravity waves coming off, okay, emanating away. The more you look at this, the more detail you see about this event. All right, we'll do this one more time because it's just so darn cool. This rapid scan stuff just blows me away. Here it comes. And look at all the different layers of clouds you're seeing here. But once again, northwest corner of PA, supercell, basically. Look at the shadow cast. You see some fog down here in the valleys, right? That storm doesn't care. And you know, just start looking for those gravity waves up here coming off these convective turrets. There they are right up in here, the beautiful gravity waves. That tells you that this convection is incredibly energetic. It's getting up into the lower stratosphere. It's exciting. It's creating waves. It's creating, you know, wave features in the lower stable layer of the stratosphere. All right. Well, enough of the animations. Let's go on here to looking at the synoptics of this system. So, you know, I like to start when I talk about a case, big scales, and then working down. So this is the surface map at basically late morning. So this is 1630Z. This is late morning, and the system is already basically initiated off of Erie. But what you're seeing is something that's fairly benign. There's no large cyclonic low pressure system. The nearest front is north of where this thing initiates, up through New York State. This really is warm sector. You've got a big ridge down here dominating the southeast and the mid-Atlantic. And this is just pumping Gulf moisture and warmth up into the mid-Atlantic region. This front is across the northern periphery of this ridge. You got cooler Canadian air up here. But this is a type of setup you tend to see for progressive derechos. You just typically have a ridge to the south, cooler mass to the north, a stationary front separating the two. All right. And something small comes through and starts perturbing the flow. That's all it takes. Other interesting thing you'll see here is what we call a lee side trough. So this is a surface trough. It's a fairly impressive one. This is a trough of low pressure extending basically down the Piedmont, out of Maryland down to Virginia and into North Carolina. And I think that's going to play a role here as we'll go through the slides. But we're just basically in the warm sector of the return flow of a large, you know, ridge to the southeast with a front to the north. Okay, fairly innocuous. Here's the upper level flow. This is 500 millibar flow. This is where you got some energy. And this flow is shown by the shaded regions here. Here you got 50, 60 knot speed max coming through basically New England with 60 knot flow coming across northern parts of Pennsylvania. And this is significant. This is significant here. And it's hard to say whether or not there is a perturbation like a short wave embedded in this. You see a little bit of something suggesting that perhaps up around Binghamton in the flow field, but there's nothing egregious that stands out. This is basically zonal flow aloft. This is the northern edge of a very, very massive ridge. But this is basically a corridor. You've got unstable air mass in place to the south. You've got a stationary front and a corridor of fast flow that's basically northwest flow aloft. And that is a setup for progressive derechos. That's a climatological type of setup on the synoptic scale. And this was enough of an issue that Storm Prediction Center was concerned about this being a derecho corridor that day. Here's, I'm quoting them, most of the convection allowing models or CAMs support one or more Boeing segments, and a corridor of damaging wind is expected. That's why they put out the enhanced outlook for this area, because it looked like at least the conditions would favor the initiation of a derecho. Okay, but they didn't know that at 6Z. Had no idea one of these was going to fire off and be a problem 12 hours later. All right, this is the deep layer shear. And this is important. Wind shear is the change in wind speed, wind direction with altitude. And if you know severe thunderstorms, and most of you folks who are chasers, this is a key parameter. You're looking for your shear. And basically, the more shear, the better it's going to be for chasing. Okay. We like to see, for supercells, we like to see at least 40 knots of deep layer shear. By deep layer, I mean 0 to 6 kilometer. You get up into 50, 60, it's like, oh boy, this could be a really interesting day as long as you got the thermodynamics. Well, the numbers here were pretty impressive for August. I mean, when you're talking about 40, 50 knots of shear across the Mid-Atlantic in August, or June, excuse me, I got my month screwed up, June. That's a pretty nice value. And you basically have got 50 knots of deep layer shear. You can see the little barbs here, the pennants, cutting across most of Pennsylvania. And that certainly was a major contributing factor to sustaining this derecho, promoting long-lived convective elements, and the merging of those convective elements. Okay, so that was good to see. Now, let's talk about the air mass itself, the thermodynamics. How unstable is this air mass? Because we are talking about morning hours here. Typically, you maximize your cape mid to late afternoon on a summer day. Okay, and you might expect to see, in the warm sector, the return flow of 1,500, 2,000 cape, something like that. I'll show you the cape in the next slide, but what I want to show you here is something called lifted index, which is basically the difference in the temperature between the rising parcel and the environment at 500 millibars. The bigger the positive anomaly, the more buoyancy you have. It's like the hot air balloon. The warmer the inside of the balloon, the faster up it goes. Okay, so the acceleration. This is at the height of the derecho. So you're here at 17Z, and here you see the thing screaming across New Jersey, creating all this wind damage. And you're saying, well, where's all the high lifted index values here out ahead of the storm? And there's only -5. That's not a, it's a decent amount of instability, but it's not earth shaking. Some of the really, really unstable atmosphere days we have here, -8, -9, -10. Okay, that's a very significant lifted index. But given the severity of the storm, basically what was feeding into it was -3, -4 lifted index air mass. The really juicier stuff is 100 miles to the south over southern Maryland. So I would say that the instability here is modest, and you know what? It's okay if you only reach moderate values at noon or 1 in the afternoon. You're on the way to further destabilization. All right. If you look over Northeast PA, you see 0 and positive values. Well, this is an air mass that's been stabilized by the cool pool of this system as it's cut across. So you've got this, dipole of stabilized air in the wake of the storm, and only modestly unstable air immediately available to the south. Okay. But the interesting thing is that the most intense convection was located in the southeast corner of the storm. So the convection was firing off where the most unstable air was located, and it was propagating in the direction of that most unstable air. This is where all the new convective growth was occurring, folks. It was down here on the very edge of this destabilizing air mass. And that's right along the Mason-Dixon line, basically. Okay. But I will say that the fact that the storm complex came off the high terrain at about 11 to noon was one of the reasons I think that this thing became more intense. Even though it was modest instability, the timing was just right for this storm. Had it come off, let's say 8 or 9 in the morning, I don't think we would have seen something very intense over southeast PA, New Jersey. there just would be hardly any destabilization at that point. Imagine what might have happened had it come off at 3 or 4 in the afternoon, with perhaps twice the amount of unstable air available, twice the magnitude. Imagine what could have happened had it been a few hours later in the afternoon. But I think it was enough. It was certainly, well, it obviously was, but just enough unstable air combined with all that wind shear was sufficient for this thing. We'll continue to explore this a bit. Now, here are the actual CAPE values. Now, these are always difficult diagrams to interpret because and these come from SPC. They try to put all kinds of things on these diagrams. You got surface wind vectors. You've got composite reflectivity from the radar. The blue shaded areas, these are areas of convective inhibition. So this is a capping layer. There's a little bit of capping here, not very extensive. And then you look at these red lines. These red contours are the contours of CAPE. All right, but I've done kind of the looking with a magnifying glass here for you. At 1 in the afternoon when this thing was coming through, the surface-based CAPE was only 500 to 1,000. And this is on the very southern end of the line. And you're like, big deal. This happens all the time. This is a daily occurrence in the summer. So what I'm trying to tell you here is this is kind of benign so far, except for the wind shear. The wind shear is crazy. But the thermodynamics, But as we will see, I believe there are other factors that help to compensate. Okay, so this is why you dig deep into these cases to kind of understand, unpack where does the devil in the details lie here. Okay, and I just wanted to show this. This is lightning. This is a Vaisala product that shows lightning history, and I think this kind of dovetails nicely with what we just saw with this reservoir of CAPE down here on the southern end of the line. Well, this is where the storm really began generating lots of lightning, right as it comes off the terrain. And starts propagating to the southeast into this unstable air that's sitting right about here. Okay, here you see the convection responding to that and starting to really generate very, very significant lightning density. And this goes back, this is 2 hours worth of lightning history here. Okay, so the colors indicate this is the oldest strikes here. These are the most recent strikes up here. All right, now let's unpack the thermodynamics a little bit more. Now, some of you who are serious chasers and understand your meteorology, I'm going to say the fancy word, the environment, the elevated mixed layer, EML. Okay, that's technical. Okay, but I know chasers, you're into this kind of thing. You see an EML. What an EML is, folks, it's an elevated layer of hot, dry air that's coming typically from Southwest US. This is where it's generated down here off the high terrain in the summer. And if the winds are right, you have winds that are, advecting this elevated hot and dry layer towards the east. Now, the further east you go, the more uncommon it is to see an EML. Chasers out here in the plains love this thing, and it's out here all the time. This is a capping layer. What this does is it holds back, it suppresses early convective growth and allows the CAPE to build to enormous levels. It's like charging a battery or a capacitor in the atmosphere. And the EML holds it back until eventually the instability is so strong that the convection has to fire off, or something weakens the cap, or something happens. Okay, but the atmosphere explodes late in the day. Well, this is really interesting. See this orange and red out here? What we're looking at are mid-level lapse rates this morning of June 3rd. And I'm like, wow, look at this. -8 degrees Celsius per kilometer lapse rates here in the mid-troposphere, all the way this far east of the Appalachians. And I believe it's an extension. This is the EML, folks, that has advected in the previous day. And a finger of this has made its way out east of the Blue Ridge. And part of this very, very unstable mid-level layer, even though the overall CAPE is low, the lapse rates are very important because lapse rates translate to updraft acceleration. And if the lapse rates are this steep, even though you might not have a lot of CAPE in the profile to work with, your CAPE is being maximized in a layer of the atmosphere that's critical to growth and acceleration, and particularly lofting and condensing liquid water. Okay. And that releases a lot of latent heat and increases the buoyancy in the storm clouds. So this was very interesting to see. And I think this really helped the system that day. You know, the last time we saw something like this was June 29th, 2012. The EML on that day was very, very well established across the Mid-Atlantic. That big, massive derecho, very similar thermodynamic setup in the mid-levels of the atmosphere. Okay, so this is where the details are on this day. You have to look very, very carefully. The whole integrated cape wasn't too high, but there was a critical layer there. The updrafts went boom once they got up into that layer. Okay, let's here's the sounding. This is the dullest sounding, closest sounding to that you know we could get to the location. But here's the EML and the sounding right here. You can see it where I've got circled. 8.3 degrees Celsius per kilometer. That's a very, very steep lapse rate. And there it is right there. But this is a hot, dry layer that has come in. Look at these on westerly winds from the Great Plains, most likely. Okay. And once updrafts got into this layer, they just really, really accelerated. Okay. And the convection took off. Now, we're getting into mesoscale now, from synoptic down to mesoscale. How am I doing on time? Can someone give me the time? Actually, hang on. I got my cell phone here. Okay. Oh my.
11:51 right now is the time, Jeff.
How many more minutes do I got?
You're good. Yeah, about 10 minutes.
All right. So. All right. Look. The triggering of this system, folks, this is interesting. This is a vorticity max. This is an area of spin. And this was moving across Lake Erie in the early morning, and it triggered the initial convection. You say, how did this form over a cool lake water? Well, it was dynamically forced, okay? And it turns out this vorticity max, look at this, can be traced back 12 hours previous to a large convective cell over Michigan. So this thing I think got triggered and survived the Appalachians because it had this nice little pocket of spin energy in the mid-atmosphere. And this thing moved all the way across Pennsylvania. So this convection was tied to that vorticity max as the system propagated across Pennsylvania. So again, not a lot of cape, but I think this storm had a lot of dynamical help to force it, okay? And I'm going to go ahead and just show you some of the fine scale structure of this storm. Look at this. Wait till you see this. Now, is that not a textbook derecho? That is just absolutely textbook. And you get the sense there's a mesoscale convective vortex up here. Beautiful, beautiful bowing line. Let's look at the winds. Here's the Doppler. Blue is approaching this radar K-Dix. Now look at that. Boom. Talk about wall of wind. That, when you see that, look out. So blue color is approaching the radar, red is receding. And as obviously the line crosses, the color spectrum flips. But wow, those orange colors, that's 70, 80 mile an hour gusts. Now those are at a few thousand feet above the ground. That's one thing you have to understand. That's not at the surface. But this is exactly how the June 29th radar presentation looked. Wall of wind as it came through Sterling, Virginia. Okay. Fine scale radar structure. Took some vertical cross sections on my software as this thing was coming across Philadelphia. See really intense echo cores here on the leading edge. And if we go here, as the storm was crossing New Jersey, you see beautiful, beautiful classic squall line structure, leading edge convection, trailing stratiform. And this is the Doppler cross section. You got really nice, what we call ascending front to rear flow. This is the convection feeding this slanting updraft in the upper parts of the cloud. And here is the descending rear to front flow. This is the cold pool here, and the air accelerating away from the radar as the bow echo passes off to the east. So this thing had textbook radar structures, both horizontal and vertical. And I'm going to skip that slide, and we're going to go right to lessons learned, and we'll take some questions. Okay. So the interesting thing about this storm, Appalachian crossing and intensifying. And so I think that little vortmax definitely helped keep this thing going. It was coupled to that as it came across Pennsylvania, and I think that helped made up for lower instability. And this is a storm that thrived in spite of limited cape, because you had an elevated mixed layer with very steep lapse rates. And something I didn't talk about, but there was a lot of storm relative flow coming into the low levels. The winds were coming in from the southeast. And matter of fact, because I know I have a minute, I'm just going to go. I want to show that aspect. Here's where you had your maximum instability. As you know, here's the storm. It's moving at 45 knots or faster from northwest to southeast. But look at the inflow. This is low level flow, 0 to 2 kilometers, directed straight into the southeast part of the line. So all this cape, all this instability, it was actually getting into the system. It was just being advected in from a little further out ahead of the storm environment. So once again, all these things helping to make up for, modest cape and producing a storm that ended up being very intense. Very strong deep shear. Yeah, that was a major plus this day. The vertical momentum transport probably very much enhanced. So there's a lot of momentum, a lot of kinetic energy in the airflow, a few kilometers above the ground this day, 50, 60 knots. And there's no doubt that the convective downdrafts were bringing some of that momentum down, tapping into that wind layer, bringing that momentum right down. That momentum was contributing to the energy of the cool pool. Okay. And folks, I love investigating derechos in the Mid-Atlantic. So if you want to reach out to me, here's my email. I have a research group, grad students at UMBC. I'm putting a blog together. It's going to be a research page on derechos in the Mid-Atlantic. I've been working on it over the summer. And it'll be great to get some collaboration, hear your ideas. If you've chased these type of things, I want to hear about it. If you got great pictures, anything you want to share with me, reach out to me, please. This is a great community. I'd like to tap into it. So there we go. We got through the hour. Okay. I'll turn it back over to this wonderful panel and let them wrap things up.
All right. Well, thanks a lot, Jeff. I don't know about anybody else. I was geeking out.
That was really cool. Yeah. I love seeing the imagery, and I feel like Dr. Halverson, there's so many that have happened this year. I think that if you didn't impact you, they went unnoticed. And also just the fact that the question a lot of times we get as broadcast meteorologists is, how do you know it's a derecho? And going over that criteria really helps out a lot.
Yeah.
Right.
And I want to mention some of the criteria are even the length criteria is kind of wonky, because historically it was 250 miles. If you go back in the literature now, it's 400. And it's like, okay. And some of the research was based on older sets of criteria. Now you got these newer sets, and it's like, it's really all over the place. The other thing I want to mention, Brent, is there's a spectrum of these events, like any other meteorology phenomena. We rate hurricanes 1 through 5. We rate tornadoes 0 through 5. We don't have a rating scale for derechos, but I think we should. I really think we should, because there are definitely low-end events, and then there are very high-end events. June 29, 2012, that was knocking up on the real severe end of things. But some of these others we get, especially the ones that cross the Appalachians and kind of fall apart, they're wimps by the time they get here.
One of the questions that we got off of Twitter, Jeff, is how are models doing at predicting these events days in advance? Have they gotten better? Are they still kind of?
Yeah, I think what we can do is we can show there's a corridor. There is a potential zone where these things could form. But until one of these things pops off, that's when the cams start working with it. Back June 29, 2012. The cams picked up on it, but not until it developed. Okay. Because the cams are initialized with radar.
Bill, did you have a question you wanted to pose? You're muted.
Oh, I wrote it on the chat to read.
Okay. So we can get that. Let's see off the chat. Bill had a question. Assuming the maximal surface winds are at the point of the curve, how often do tornadoes form in these types of derecho events, and where would you target one along those bow lines?
Fabulous question. Tornadoes do develop. They do develop in connection with bow echoes in general. Now, I'm being a little more broad. I'm saying bow echoes. So that doesn't necessarily mean derecho, because derechos are just a tiny subset of all bow echo type of systems, what we call QL CSs, quasi-linear convective systems. Okay. The tornadoes tend to form at the what we call lobe and cleft parts. So you have a bowing part, and then you may have an indentation along the line, north of the bow, south of the bow. It's in those indentations where the bow takes on an S shape. That's where you're going to see these little mesocyclones or small mesocyclones, and that's what's actually distorting the bow into an S shape. So the indentations are where you look, and there's a lot of work coming out of Sterling NWS down there, and there are some papers on this. 15-20% of all tornadoes in the United States are thought to be generated by QLCS bow echo type structures. And that's a fifth of our tornadoes. Now they tend to be low intensity. They're F0s, F1s, and very few F2s, hardly any F3s. They're hard to chase because they're so ephemeral. They're so transient. And to be honest with you, I don't know if I'd be getting into a derecho outflow looking for tornadoes. I just think that's kind of nuts, because there are trees and power lines coming down and things flying through the air, and you're not going to see these tornadoes. They're going to be rain wrapped, and they're going to be tough to find. Good luck.
So
go for the
heed
super.
those warnings, storm chasers.
Exactly. Did we have any other questions from social media or from YouTube?
Yes, we have some. I think we had a follow-up question, which I think you just answered. Most are rain wrapped, right? When dealing with tornadoes and QLCSs.
Oh, yeah, they are. Now, you might see a tiny little wall or something, but like I say, by the time these things get warned, these tornadoes get warned, they're done. They're just so short-lived.
In the one that we had that moved through our area, looking at the radar, obviously it looks like there's a bunch of rain there, but it ends up a lot of that rain even being elevated at times. And so on radar, it looked like there was a lot of rain with it, but it barely produced hardly any rain for our area too. How, is that's pretty common, I'm assuming, with these derecho events that come through, is that rain is just, a lot of it's moving so fast, it just stays in the clouds.
Yeah, a lot of that rain is horizontal in the wind. I mean, it's just. I was in that 2012 derecho, and I've never experienced precipitation going sideways like that. It was just being literally shot by little gusts. Like, it hurt to be out in that. That is not fun, having rain slung at you at 70+ miles an hour.
About, is there one more question we need to ask before closing?
Actually, I had two more, if that's all right. One, do derechos tend to move more west to east, or can they move north to south?
I would say the climatology says basically northwest to southeast. Let's split the difference. A lot of these are northwest flow aloft events. They can take a right turn. Some of them do, and this one over PA took a bit of a right turn. The June 29th took a bit of a right turn. So the motion became, let's say, initially west to east to more northwest to southeast over time. I have seen one do a right turn completely, and it did start hooking north to south. So they can do it.
Okay.
And that's because of propagation. The convection is developing towards the south, because that's where the more unstable air is located. So the convection is propagating in the direction of the greatest instability. That's why they turn right like that.
I have one more question. Do you think we still have time?
Absolutely.
Good.
Excellent. All right, guys, this is a good one. This is one that I get a lot recently from family members. I almost never heard of derechos when I was growing up. Is this a new term, or are they just becoming more common with climate change?
Oh boy. The late 1800s is when the term was first coined, and certainly, I think it was certainly forgotten for decades. Wasn't really back in the even the meteorological establishment, not until the mid 80s. The paper by John Hurt re-brought that term. Now, climate change, boy, that is interesting, isn't it? We always seem to finish on a question with climate change with these things. I don't know of a single study out there that has looked at this connection at this point in time. Hell, we can't even agree on a definition of these things, much less say how have they been trending over the past half a century. I can postulate this. These things are in the summer, they are intimately connected to heat waves. They really are. These things ride the northern periphery of a giant heat dome across the US. You've got super unstable air mass over the southern tier of the country. These things are forming on the northern edge. If these heat domes are becoming more intense, more frequent events, could we say that perhaps the storm systems that are feeding on them might become more frequent or more intense? I'll just leave it at that. Think about that. Okay. Think about that as a possibility. I don't know whether it's right or wrong, but it's possible. It's possible.
Okay. Well, Jeff, we certainly thank you for your time and expertise. As I said, I've been geeking out. I hope everybody else has on all of this. We will wrap this up here just to make sure that we don't take people's time too much. You already provided your email address. Is there any other way that folks could get a hold of you if they wanted to?
I think the email is really the best way. And it's right here again. I'm on email 24 hours a day. That's really the way to do it. I'm not an active Facebooker. I don't have my research on a Facebook page, but once I get this blog up and going on the Dayrachos, I'm hoping to attract people to that.
Okay, great. Well, Brent, I guess we're close to wrapping it up. Do you have any more to say about our upcoming stuff?
Yeah. So let's do that. Let's talk about the upcoming events that are going to be coming in. So first up, the next one is going to be coming. You guys see that October 31st. So Halloween, we've got a special guest, Jeff Orrock from National Weather Service Wakefield. And this is going to be hosted by our sister station in Richmond, Jim Duncan from NBC 12. And again, these will be starting at 11 a.m. once again, and you'll be able to see that. Then coming up November the 7th, we have Karen Kasiba. Is that correct?
Kasiba?
Kasiba. I knew I was going to mess up. Kasiba for the Center for Severe Weather Research. This is going to be super fascinating too. Aubrey Urbanowitz from WHSV in Harrisonburg will be joining us to host that event. Always going to be really cool. And then on November 14th, also on a Saturday, again, these are consecutive Saturdays, we're going to have a storm chaser panel. And this is going to be really cool. And of course, we had Dr. Jeff Halverson today, who you just saw. And this has been a really interesting, very, very cool presentation. So thanks so much for joining us, Dr. Halverson, on this. Has been very fascinating.
I have a question. Are these recorded and available for viewing?
Yes. So these are going to be recorded. These are recorded on our YouTube, the YouTube channel that has been set up, which is Mid-Atlantic Chasercon. And we'll send out a link to all that once it goes off, once we go off live, that'll be processed and you'll be able to watch it all the time. In fact, we encourage you to, check out the comments and even leave some comments on the video itself, because I'm sure it'll get viewed a lot more than just right here.
Right. Good.
Chris, do you have any comments?
Well, I thank everybody for their help. I know Bill and Peter have been monitoring social media for our questions. Brent, thank you certainly for pushing the buttons and keeping us on track here. And Jeff, just thank you again for appearing for us. And you're welcome to come to ChaserCon anytime when we have it scheduled again.
I sure will. Thank you very much.
All right. Well, we'll wrap it up here and we'll look forward to next Saturday. We'll be actually talking about maybe what we would call the forgotten tornado event of 2011. There's a lot of focus on the April 27th event, which was pretty devastating. But 11 days earlier, there was a tornado outbreak in eastern North Carolina and Virginia. We'll be talking about that. So Thanks a lot, everybody.
Thank you.
Thank you.